Now we will talk about backpropagation. So we have discussed it earlier. There is a mechanism of feedback when it comes to neural network, which is not usually there in the other algorithms. And this feedback mechanism essentially helps us out to improvise over the time. And how it does with the help of backpropagation. Now, what is backpropagation? So we have seen in the previous slides how the network was, or how the information was processed in a neural network. So information was processed where we have input layer which interacts with the input or the surrounding, and we have the hidden layer which processes that input which is extracted from the surrounding. Then we have output layer where we transform the input data and convert it to readable output, and that readable output is what we get as an output. So basically this is how a neural network works in the feed forward manner. So this is what a feed forward neural network is. Now there is a phenomenon in neural network where it wants to improvise over the time, and this is how it can be done with the help of backpropagation. So backpropagation is a mechanism where the network sees what is an output and it compares that output with this actual output for that particular data. And as it compares, so it understands what kind of lack of accuracy is there in the output generated by the neural network and the output which is there, um, actual, like what is the actual output, which what is the desired output. So as we see that the algorithm understand what kind of problem is there, what kind of lack is there. So in order to improvise this, it goes in the backward direction to improvise that particular error, and to minimize the error it will move in the backward direction. So it will just keep on adjusting the weights in this backward direction, and it improvises over the time. So backpropagation consists of the repeated application of two passes basically over here. So in this step, the network is activated in on each one activated on each on one example, and the error of each neuron, the output layer is computed. So what happens? Uh, it actually identifies the error at each level of neuron, and in this step, the neural network is used for updating the in the forward pass. It basically, so backpropagation consists of repeated application of two passes. First is forward pass, and second one is the backward pass. As we saw in the forward pass, the network is activated on one example, and the error of output layer is computed at that example. And in the backward pass, in this step, the network error is used for updating the weight. So it wants to update the weights, and starting at the output layer. So initially it will start the update of the weights at the output layer. The error is propagated in the backward direction through the network layer by layer. This is done by recursively computing the errors and finding out the local gradient at each level of the neuron and reducing that gradient so as to get minimal error. So this is how backpropagation actually works. And MLP, multi-layer perceptron, we can see the forward propagation here. In multi-layer perceptron with one hidden layers computes the function. For example, we are applying a sigmoid activation function, as it is an sigmoid, as we discussed that it is a multi-layer perceptron. So we are applying sigmoid activation function over the activation function, or the function that we are getting for a single level of neuron. So sigmoid activation function of xw1 plus b1 into w2 plus b2 is the value, as we can see for the first layer at the one hidden layer values. A multi-layer perceptron with two hidden layer computes the function, that is, it is done by applying two sigmoid activation function over the function or the value or the z value. And generally, an multi-layer perceptron with n number of layers will have n number of sigmoid activation function applied over the hidden layers or the input data. Like this, during forward propagation, the activations or the output from neuron of one layer are passed to the neurons of the next layer. So this is how a forward propagation in multi-layer perceptron happens. And in the backward propagation, what happens is, as you can see, that we are applying multiple level of function over each and every input data, or that linear combination of input data. In the first hidden layer, we can see linear combination onto which we are going to apply our hidden our activation function. In the second also, we are applying two activation function over that additional activation function. So this actually keeps on happening. Okay, so as we add more and more activation function, more and more uh, as we add more and more layer, for each and every layer we will have to have more activation function for each and every neuron, which is actually kind of recursive in nature if we are seeing. So during now we'll talk about back propagation. So if we have understood, like, we have applied multiple level of functions on the output of each and every hidden layer recursively within itself. Okay, so it is going kind of incognito. When we talk about applying this function, the function is applied incognito like that, and this is how the output is processed in the forward propagation part. Now let us talk about the backward propagation part, in which during this backward propagation, during training, the error of the loss function is calculated at the output layer. Okay, at the very output layer we calculate the error, and we need to minimize this error. Now how can we minimize this error which is happening at the output layer? So in order to minimize this, we need to change so error has happened because of certain assumptions of weight. So we have initially done random assumptions of weight, as we discussed in the first calculation part. So uh, we are doing random assumptions of weight. So as we are doing random assumptions of weight, we need to change these weights now, because the random assumptions are giving us wrong values. So in order to change these weights, we update this weight based on the gradient or the error that is happening. So error of the loss function can be minimized by updating the network parameters, which is weights of the connections between the neuron, and the gradients of this loss function is calculated with respect to the weights using this back propagation algorithm. Now at every level we are going to partially derivate that particular error or gradient based on the previous weights. So each neuron will be associated with a certain level of weights, and we will do partial derivative in order to get that weight, and the partial derivative is done in a way that the gradient has to be minimized at that level. So we will apply the gradient descent at each and every level of or each and every level of the parameter to update the weight performed by using the weights and bias. These steps are continuously repeated up to a fixed number of iterations, or until the differences of errors are optimal or acceptable. So in two successive iteration is less than predetermined threshold. So we can keep a threshold below which we can accept that particular data, or we accept that level of convergence at that particular point. So on this in this back propagation, basically this iterative this keeps on happening iterative for this happens iteratively to adjust the weights in such a way that the gradients or the weights are minimized. So back propagation, we have two parts, that is network activation, which is feed forward part, and the second part is error propagation or the backward step part. So in both the parts we are basically getting this data, or we are propagating the data. Back propagation adjusts the weights of a neural networks in order to minimize the neural network, that is total mean squared error. So the objective of this back propagation is to reduce the error. Usually it is mean squared error, and that is done with the help of this partial derivative with respect to the weights that we are going to update, or the weight that we are going to change at each level. Now back propagating errors. So back propagating errors at multiple nodes, both the output nodes can have errors. So T1 T2, let us consider it as predicted output. O1 O2, let us consider it as actual expected output, and even E2 are errors. So in our case here, E1 is equal to T1 minus O1 and E2 is equal to T2 minus O2. And our objective is to reduce this value E1 and E2 so as to have a very closer values of T1 and O1. So E1 is split into two using the below ratio, as we can see W11 upon W11 plus W12 is to W12 upon W11 plus W12. So here even value, as we can see, E2 is split into 2 using the ratio like W21 upon W21 plus W22 is to W22 upon W21 plus W22. So this is these are the two splits for each E1 and E2. E1 is the error corresponding to the value T1 and O1, and E2 is the error corresponding to the value T2 and O2 for the actual and the predicted value. Now we are backpropagating the errors, backpropagating the error in case of multiple layers. The error which is split as per the proportion will again be split based on the weights in the previous layers until the input node is reached. So for example, we have input layer 1, input hidden layer 2, and output layer 3. So whatever is the proportion, or when the errors will be split as per the proportion, will again be split based on weights in the previous layer. Like once the propagation or the weights have been adjusted here, it has to be done for the consecutive previous layers also. So E hidden one will be again be equal to sum of split errors on links W11 and W12. So E1 into W11 upon W11 plus W12 plus E2 into W12 upon W11 plus W12. Now this is the hidden layer error, and it is again dependent on the value of error 1 and error 2 which we have received recently. Now propagate the error back to where they were originated in order to correct the output. So if you want to correct the output, current output, the weights of the previous layer are not sufficient to be getting updated. We need to update the weights of the previous layer as well. So it is not just about the current layer, it is the weights of the current output layer, but it is again the weights of the weights which are passed on to the hidden layer as well. So the following illustration, like we can see that here in this illustration, we have three simple layer: input layer, hidden layer, and output layer. And the weights of this output layer is getting identified or adjusted based on the value of the output layer. Output E1 is 1.5, E2 is 0.5. We need to reduce this errors, or in order to reduce this error, we need to change the weights again. And again, you can see the newer weights will get optimized based on the previous weights and the gradient value or the error value. Now this has happened or at this hidden layer or the hidden layer and between the hidden layer and the output layer. Now this has to happen again in the input layer and hidden layer. So it is going to happen in the consecutive next or the previous layer as well. So here also W11 the weight needs to be optimized. Now if we optimize this at this level also, then only we will be able to get an output which will be less of error. So this is what is expected. Now, if we talk about the matrix representation of backpropagating error, so the starting point of error that emerges from neural network at the final output layer. Here we only have two nodes in the output layer, so these are E1 and E2. E output is equal to E1 and E2. The first hidden node's error has two paths contributing to it from the output layer. The error signals E1 into W11 divided by W11 plus W21, and E2 which is W12 divided by W12 and W12, which is these are the two errors that we have talked about. Now the second hidden layer node has two paths contributing to its error, that is E1 into W21, W21 plus W11, and E2 into W22 divided by W22 into W. So this consecutively keeps on adding if you add multiple hidden layers, and that's how the hidden layer ratio also becomes. So W11 upon W11 plus 2, W12 upon W11 plus 1, 2, and W21. So here we are getting a matrix representation of an error. So this is how finally the error matrix looks like. So error matrix is now based on the two level of weights optimization has been done. Now the multiplication of output errors En with linked weights Wij, the larger the weights, the more of the output error is carried back to the hidden layer. So as we are increasing more, or the weights are more in the output layer, if it is more, so output error is carried backward to the hidden layer. Now where we have E1 which is dependent on W11, E1 into W11, W11 plus 21 would become much simpler as E1 into W11 than the transpose of matrix itself. So Here what is happening, the multiplication of the output errors en will be linked with output or the weights wij, and larger is the weight, more of the output error is kind of processed or carried backwards in the hidden layers. So the matrix approach to propagate the error back can be represented by using hidden error is equal to wt into hidden output into error of the output. So this is how the equation of the hidden layer is. So for hidden layer, the transpose of the hidden weights, output weights of hidden, the transpose of the output weights into error of the output will give us the error of the hidden layer. And this is how the matrix transformation works. And due to this, the weights are kind of computed. So now we have the challenge of getting an error at each level, and this can be done with the help of this formula, which is a matrix representation of the propagating errors.